Assalamu alaikum. It's been a long time, but we are back. It is setting up. Okay. So welcome once again. It's been a while. Anyway, you did the midterm. I'm grading. We'll see how it comes about. In the meantime, we continue with our lectures. Last week, we looked at 17.2, 17.3, 17.4. We are in complex numbers, complex analysis. We've looked at functions, sets in the complex plane. We looked at functions and mapping, complex mapping. Okay. So now this week, actually from now on, we'll be doing 2 sections per, this camera is shaking. I hope not too much. Okay. Do I need to adjust it or it will be okay? Just one moment. Let me just adjust. No, I think it's going to be okay. Anyway, fine. So, I was saying that we now, so for the next several weeks, we'll be looking at 2 sections per week. So this week we'll look at 17.5 and 17.6. Now 17.5 is looking about Cauchy-Riemann equations. In fact, basically, since the last time we were looking at when you bring in functions, then you bring in calculus, okay, of complex numbers. In other words, you're talking about limits, continuity, differentiability, analyticity, okay? And functions that are analytic in the whole complex plane, they're said to be entire, okay, like e, the complex exponential function, etc. So anyway, now there is something called the Cauchy-Riemann equations, which we abbreviate by CRE. So the first theorem here is suppose f of z, a function, complex valued function f of z equals u plus iv is differentiable at a complex point, z equals x plus iy. Then the first order partial derivatives of u and v. These are first order partial derivatives of u and v with respect to x and with respect to y satisfy what we call the Cauchy-Riemann equations. The Cauchy-Riemann equations are basically the first partial derivative of u with respect to x equals the first partial derivative of v with respect to y. These are equal. And the first partial derivative of u with respect to y equals minus the first partial derivative of u with respect to x. That's the theorem. So we look at 2 examples here. First example, show that f of z equals z squared plus z is entire using Cauchy-Riemann equations. So basically, we just need to show that these equations are satisfied for this, for all z. Okay. So what do we do? What we did the last time. Z is given by x plus iy. So you replace this with x plus iy. And then this one x plus iy. So you get the function in terms of x and y. So you'll have f of z equals z squared plus z equals x plus iy squared plus x plus iy. This you open, you just get x squared minus y squared plus 2ixy plus x plus iy. Then you bring the reals and the imaginary together. So the reals are basically x squared minus y squared plus x. And then the 2iyx and the iy is that. So this forms u and this is v. So u equals x squared plus y squared plus x. And v equals 2x plus y. So now we take first partial derivatives of, now where have I gone here? So now we need del u, del x. So you differentiate this with respect to x partially. So you differentiate with respect to x, you will have 2x, this is 0, 1. So it's 2x plus 1, okay? Which is exactly this, okay? The next, you differentiate this one with respect to y. So you will see that this is like a constant, so it will just be 2x plus y. So those two are equal. We finished, okay? So del u, del x equals del v, del y. Next, we find this one. Now, where have I gone? Sorry. We find these ones. So, del u with respect to y, you differentiate with respect to y, this will just be minus 2y. This is 0, this is 0. Then you differentiate this with respect to x. It will be, this will disappear. It will just be 2y. Okay? So, this is what you have. You have minus 2y and you have 2y. And these are negatives of each other. So del u del y is the negative of del v del x, which is these Cauchy-Riemann equations. They are satisfied for this. Hence, this function is analytic everywhere for all z, so it's entire, in other words. Since the Cauchy-Riemann equations are satisfied, then the function is analytic, for all z, and therefore it's entire. Example number 2, show that f of z equals 2x squared plus y squared minus x is nowhere analytic. So in other words, the Cauchy-Riemann equations will not be satisfied, and anyway, something happens. So we need again to find del u del x, del v del y, del u del y, del v del x. So here now we have, this is our u, and this is our v. So if you take del u del x, it will just be 4x, and that's it. Then del v del y, del v del y is this one. You differentiate with respect to y, you get 2y. This is 4x, this is 2y. Go to the next page, you see. So the u is 2x squared plus y, and v is this. You differentiate this with respect to x partially, you will get 4x. You differentiate this partially with respect to y, you get 2y. These two are not equal, right? So del u del x is not equal to del v del y. Next, we can check the other one, but we don't need to, because that's it. We can say already it fails. But anyway, del u del y, it will just be 1. And then del v del x, it will be minus 1. And these are negatives of each other. So one of them is satisfied, one of the Cauchy-Riemann equations, but the other one is not satisfied. So we can say, since del u del x is not equal to del v del y, then the function is nowhere analytic. I mean, it doesn't satisfy this theorem. The theorem says that you must have this. You know, Cauchy-Riemann equation must be satisfied, so this fails. And anyway, one last thing I can say is this. This function is not analytic, actually, for all z. It's not really analytic, actually, anywhere. However, when will this be equal to this? When is del u del x equals to del v del y? When 4x equals 2y, which is y equals 2x. So, however, along the line y equals 2x, the function is differentiable. The Cauchy-Riemann will be satisfied along that line only. Of course, if you go outside the line, then you get a neighborhood where it is not analytic, because it will give you values for which this is not equal. Therefore, this is differentiable, yes, on this line, but it's not analytic there. That's an interesting observation to make. Okay, next theorem. Suppose the real valued functions u and v are continuous and have continuous first order partial derivatives, the CRDs, in a domain D. If u and v satisfy the Cauchy-Riemann equations at all points in D, then the function f of z is analytic. Now notice here we're saying continuity of this and the Cauchy-Riemann equations are satisfied in D. So there are two things. The Cauchy-Riemann equations, one, and that this u and v are continuous, okay, in that same domain. Then we can say this function is analytic in D. Example 3. So what does it say? So show that f of z equals x over x squared plus y squared minus I over y divided by x squared plus y squared is analytic. So what do we do, ladies and gentlemen? Well, what we'll do is we take, where u is x over x squared plus y squared, and v is minus y over x squared plus y squared. Take the Cauchy-Riemann equations, partial derivative. So when you differentiate this partially with respect to x, you can see you'll apply quotient rule. So you just differentiate this one, you get 1, you multiply by this, so you get x squared plus y squared, minus, you differentiate this, you get, with respect to x, you get 2x, you multiply by this x, this is minus 2x squared, divided by this one squared, that gives you del u del x. So if you simplify, you just have y squared, and then this is minus x squared, divided by that. Next, del v del y, you differentiate this partially with respect to y, what do you get? Well, again, you differentiate this, you get 1, you multiply by this, you get what? Minus x squared minus y squared. Then, minus, you differentiate this with respect to y, you get 2y, which you multiply by this is 2y squared, but then you are subtracting, so it becomes plus. And so now this simplifies into y squared minus x squared over this, which equals to this. So these two are equal. So the first set of the Cauchy-Riemann equations is satisfied. Now we need partial derivative of this with respect to y, and then this with respect to x. So next, what happens? If you differentiate this with respect to y, what do you get? Well, the first part will just be this 0. Multiply by that goes, so minus, you differentiate this with respect to y, you get 2y. So you have minus 2y multiplied by the x that remained, this x here. So this is what you have for del u del y. Then del v del x, you differentiate this with respect to x, what happens? Well, with respect to x, this is 0, you multiply by this, so it's 0 minus, you differentiate this, is 2x, which you multiply by this, it becomes plus 2xy. So this is plus 2xy over x squared plus y squared squared. And then these two are negatives of each other, so the Cauchy-Riemann equations are satisfied. Yes, it's true, they are satisfied. However, there is a catch. That u, what is u? Is this continuous? This is continuous except when x squared plus y squared is 0. When x squared plus y squared is 0, right? So basically, what we need is, so the Cauchy-Riemann equations are satisfied except at x squared plus y squared is 0, which is at z equals 0. Hence, we conclude that this function is analytic in any domain that does except where z is 0. That's it, ladies and gentlemen. Okay, let's see how far we can go with the next one. Now the next is what you call harmonic function, so probably I can define very quickly. So, a real valued function phi of xy that has continuous second partial derivatives in a domain D, it satisfies Laplace's equations. These are basically the Laplace's equation. Del 2 phi del x squared plus del 2 phi del y squared equals 0 is said to be harmonic in D. So in this case now, we have the Cauchy-Riemann equations. Now we take the second partial derivatives. So suppose theorem 17.53 says that suppose the complex function f of z equals u plus iv is analytic in a domain D. Then the continuous functions u and v are harmonic. That is, you take the second partial derivatives of u with respect to x, second partial derivatives of u with respect to y, you add up, you get 0, and then del v, del 2v, del x squared plus del 2v, del y squared is 0. That's one. Then the next thing to say is, so they are harmonic, provided these are continuous. That's one. Two, that you can actually find, if you have u of x, you can find v of xy, and conversely. So u of xy is the conjugate, it's actually called the complex conjugate harmonic function of v of xy, and conversely, v of xy is the harmonic conjugate, actually I should say harmonic conjugate of the function u of xy. So basically, if I give you a function, I can give you this. I tell you to show that it's harmonic, so you need to do this, and then I ask you to find this one. So example number 4 is that illustrates that. I don't know if we have time to look at it. So what it says that, one example, verify that the function u equals x cubed minus 3y squared minus 5y is harmonic. And number 2, find the harmonic conjugate of the function v of xy. That one. Okay. Now, ladies and gentlemen, I think we should take a break here because we may run out of time. Right? So we just take the partial derivatives very quickly. Okay, fine. So del u del x is, you differentiate this with respect to x, you get 3x squared minus the x disappeared, 3y squared. We are finished. Okay. Next, you differentiate now the second time, you just get 6x. This is 0. And now you take again, with respect to now y, what do you have? You'll get del u del y is minus 6y, xy minus 5. Take the second partial derivative, you get minus 6x. When you add these two, you get 0. This means hence u is harmonic. Okay, ladies and gentlemen. Okay, then the second part, I'll come back in the second session. So let me take a break there. Okay, bye-bye for now.